Right, welcome back Physics 30. Today's lesson is lesson number 3 of Unit C Part 2 booklet. And the person that we're going to discuss, we learned about the scientist before, back in Unit B, Millikan. If I give you a little bit of recalling about Millikan's contribution for the modern physics is, he's one of the scientists who discovered the relationship of our elementary charge. He used oil drop, and when it comes to those oil drop, he charged some of those oil drop between the charge and parallel plate, and from there we could get as the oil drop gets bigger or smaller, they increase or decrease evenly. And those slope, rise over run, was turned out to be elementary charge, 1.60, 10 to the power of negative 19. Now, Millikan play a huge role again when it comes to photoelectric phenomena, photoelectric effect. Now, one thing that I want to point it out is, he did not against the idea about photoelectric equation and phenomena. He basically verified. That means his experiment and discovery supported at one point. Millikan verified Einstein's photoelectric equation using basic cathode and anode and back voltage. This back voltage is what I want you to understand. Without further ado, I'm going to explain this picture first. So, as you can see, we have waves, but I'm gonna draw it as a particle, photon, because photon, like I mentioned before, it is wave having capsule, particle. So when photons collide cathode, and if we exceed the energy, so if the incoming energy is bigger than work function, which is digging up electron from this metal, from the cathode, then it has an ability of sending electrons to the other side. It is like shooting situation. However, what Millikan did was, he applied back voltage. Back voltage. That means apply the reverse flow of polarity. Then what's going to happen is, electron will eventually stop, and yes, it will drop back to the cathode. This stop is important because we're going to refer this as a stopping voltage. And he found that as the back voltage increase, the deeper the electron do not have enough of kinetic energy to reach to the opposite side of the plate, and if you increase more and more and more, electron will eventually stop and drop back. In this situation, current will be decrease. As current decreases, the back voltage basically and eventually reach to the point where I value is equal to 0, because you don't have a flow. So imagine Q over T, Q is 0, something like that. And we call that specific number as stopping voltage. Even if the surface electron have lost all their kinetic energy by the time they reach to the other plate, you may notice that at this point, current is 0. So there's an equation. If the kinetic energy of electron that is shooting from cathode is calculated to be equal to my potential energy, but it's a back voltage potential energy, then if you guys remember this delta EP, we'll learn that in Unit B, EP is equal to QV situation. You can substitute that formula in. So eventually, EK max, which is maximum kinetic energy of the surface electron, that is equal to Q which is magnitude of the charge of photoelectron, V stop, which is a minimum back voltage that is required to stop photocurrent. So it is a simple relationship when it comes to connecting that left side and right side. Let's do one quick example. When 4.03 electrovolt photons are shown on a metal, stopping voltage is 0.707. Determine the minimum frequency to emit electrons from metal. So one thing that you need to understand is we're trying to find out minimum frequency. And minimum frequency is basically one way of asking W is equal to HF0. We're trying to find out that W situation. Now, let's write down what is given basically. We know that incoming energy is given 4.03 electrovolt. That is shown on a metal. Stopping voltage is 0.703, so we can actually find out the kinetic energy of that surface electron, which is QV stop. Then, once you calculate those two, we're gonna have a certain joule. So let's do some conversion first. 4.03, remember that this is a electrovolt. 1 electrovolt is equivalent as 1.60 10 to the power of negative 19. So 6.448 10 to the power of negative 19 joule is what we have for incoming. And Q, which is 1.60 10 to the power of negative 19 times by stopping voltage 0.707 is equal to 1.1312 10 to the power of negative 19 joule. Now, you need to understand this. My incoming, so this is a conservation of energy. Incoming energy should be combination of work function plus EK. Work function, if I rearrange in that perspective, is difference between those two energies. So work function is equivalent to 6.448 10 to the power of negative 19 minus the previous one, which is 5.3168 10 to the power of negative 19 joule, and that is equivalent of HF0. So to find out my minimum frequency, threshold frequency to emit electron from this certain metal, we are basically isolating our Planck constant. Then we're gonna get 8.3 significant digits, so 0.2, 10 to the power of 14 hertz. That is our minimum frequency for our work function. One thing that you need to understand is I accidentally put some wrong work procedure in our work booklet as a PDF file. This value is the correct value. So have that in your mind. That needs to be modified. Now, let's go with Millikan's experimental result. So basically, he found graphical relationship like what we learned previous to this lesson. Millikan discovered a linear relationship. So whenever you think about linear relationship, like I mentioned on last lesson video, I ask you to understand that y is equal to mx plus b, and m is our slope, and x and y, those are the variable. Y is dependent variable, x is independent variable. So here's what you put. For y-axis, he put EK max, and that could convert it from our QV stop. So it is convertible. And we measure QV stop first and then convert it simply into kinetic energy for each of the plot, if that makes sense with you. Now, when you think about X is incident frequency. So it is basically referring incoming EMRs. F. It's not equal to F0. So he found and basically rearranged, if you will, into EK is equal to HF minus W. The way this come out, if you want to know, it's incoming energy that is equal to W plus EK. And we're basically isolating this as Y. So EK that is equal to E incoming minus W. That's why this minus W that you see over here is actually your Y-intercept. And as you may notice, it is negative. So no wonder Y-intercept is located at down here. And this is my W value. On the other hand, in order to have a negative in Y-intercept, you may find that we need to pass x-axis. So this is my x-intercept, and when it comes to specific situation like this, EK max as Y, x-axis at incident frequency, then F0 become our x-intercept. That's a minimum frequency. Think about that as a threshold frequency. So this is honestly as what we learn. I may just put that H in here as experimental constant. So in diploma example, if you have your plot, it is good idea to double check your X value, Y value, intercept value, and do analysis. And you have those opportunity as soon as you get to this first homework question. You need a ruler, you need to analyze some of the data. Other than that, that is our conclusion for today's lesson. I want you to work on the question on workbook page 45 and page 46.